So the sampling theorem is very important. It tells us how to maintain this one-to-one correspondence between the time domain and the frequency domain, or in other words, how to avoid aliasing. When we avoid aliasing, when we look in the frequency domain at the spectrum of our sampled signal, we can kind of see the spectrum of the original signal kind of sitting there in the middle of the sketch. At 0 DC, we see the triangle or the rectangle or kind of the cartoon different examples we've been looking at. We see that original spectrum sitting there. So we know that the sampling theorem tells us how to avoid aliasing. What we're going to work out now is exactly how to go from the sampled signal back to the continuous time. We are going to look at this thing that we call ideal reconstruction. How do I take samples and go back to the original continuous time signal? If we can do this, then we feel good that the sampling process hasn't distorted anything or removed any information, because if I can get back to exactly what I started with from just samples, then nothing has been lost. So we're going to talk about ideal reconstruction, which is this process, going from a sampled signal back to our original continuous time signal x of t. The way that we're going to think about this problem is we're going to think about it in the frequency domain. And the way we're going to think about it is summarized here in this last bullet. Given the spectrum of the sampled signal, what do we do to get back to the original spectrum, which is equivalent to getting back to the original temporal signal that we had? So if I can get back to my original x of omega, that is equivalent to having my original x of t, because x of t and x of omega have this one-to-one correspondence. So really what I'm saying here is, given the spectrum of the sampled signal, x sub delta of omega, how do I get back to x of omega? So here's a little, again, a cartoon sketch of how we're going to think about this. Again, let's think of our original spectrum, x of omega, as looking like a triangle right here. So when I have a signal in the frequency that looks like this triangle, we know what happens when we perform sampling. The impulse sampled signal, sketched over here, its spectrum looks like the original spectrum shifted up and down the frequency axis an infinite number of times, and then there's also this 1 over t sub s scale factor sitting there. So our question becomes, how do I take this and go back to this? How do we make the sampled spectrum look like the original spectrum? Well, it's kind of obvious. What do we need to do? We need to be able to get rid of all this stuff out here. We need to get rid of all this stuff out here. And we also need to apply the proper scale factor. This 1 was a 1 originally, and it turned into a 1 over t sub s. So as we're removing these images, all these extra copies of the original spectrum, we also need to apply the proper scale factor to go from 1 over t sub s back to 1. So the way that we're going to do that is with a filter. We're going to apply a filter that in the frequency domain rejects all of this and rejects all of this. Another way of saying it is we are going to use an ideal reconstruction filter that perfectly passes just this part of the spectrum and whose gain over that part of the frequency domain has a gain of t sub s. So it cancels out the 1 over t sub s and gets us back to a 1. This filter look like? It looks like this. This filter right here has a frequency response that will perfectly pass the part of the spectrum that we want, the middle part, the part centered at 0 up to omega s over 2 and omega s over 2, and it has a gain of t sub s. So it cancels out the 1 over t sub s. 1 over t sub s times t sub s gives us 1, and it restores us to the original gain that we had. So this is what we call the ideal reconstruction filter. In the frequency domain, it looks like this, and you can tell that it will reject all the images out here because this filter has a gain of 0 from omega s over 2 all the way up to infinity, and it will reject all the images out here because this filter has a gain of 0 from minus omega s over 2 all the way down to minus infinity. So this is the filter that we want to use to perfectly reconstruct the original continuous time signal x of t from the sampled version x delta of t. In the frequency domain, this is very easy to picture what's going on. We're just blowing away all those images, passing the original spectrum, and applying the appropriate gain. In the next video, let's actually work through what's going on in the time domain. And what's going on in the time domain is something that we call ideal band-limited interpolation. Some people also call it sinc interpolation. Let's work through what this filter looks like in the time domain and understand what's going on with the time domain version of filtering, which is completely equivalent to the frequency domain, but we want to understand both pieces of this reconstruction process, both in the frequency domain, as seen here, and in the time domain, which we'll do in the next video.